Welcome to the video key for Quiz 5. Okay, so starting off with number 1, we're looking at a situation where we've got this reaction to equilibrium and we add water. We want to know what happens if the equilibrium is disturbed. If it goes forwards, backwards, if it's not changed at all. So looking at this, it's the Chladni's principle problem. So whenever you have this, you want to write the Q for the reaction first. So you look at this reaction and we've got the concentration of chloride ion. We've got to square that because we've got that coefficient of 2. We've got the concentration of iron 2. And we don't have the concentration of silver because that's a solid, so the activity is equal to 1. And the left-hand side, we've got solid iron, so activity is equal to 1. And we've got solid silver chloride, so activity is equal to 1. So really the Q is just a product. Okay, so we look at this and see how is this going to be affected if we add water. So if we have water, all the things that are aqueous are going to have their concentrations go down. So if we look at this, at least initially, what's going to happen is the concentration of chloride goes down and the concentration of iron 2 is going to go down, right? Because we're diluting them, we're adding water. So if they go down, that's going to make Q smaller. So at equilibrium, we know at equilibrium, we had a situation where K equilibrium is equal to Q. But we just made Q get smaller. So if Q got smaller, now K is bigger than Q. If K is bigger than Q, we know we have to react in the forward direction. So if we go in the forward direction, we're going to be eating up some of this solid iron, and so it is going to decrease. We'll use the same logic on number 2. We're at equilibrium, we add sodium chloride, it dissolves, so we're going to increase the concentration. In this case, we're going to increase the concentration of chloride ion, right, because we dissolved sodium chloride. So sodium ions don't matter, they're not in this equilibrium, but chloride ions go up. So if we in this case, all we did was make the chloride ions go up, which means Q is going to be a bigger number, which now K is less than Q. If K is less than Q, we've got to go this way. So so another way of saying this is K is smaller than Q. So the reaction goes backward. We're going to start making some iron, so it's going to increase. 3, we're at equilibrium. We add some more silver metal. So we look, we're adding silver metal. We're adding this species here. And if we look, that does not appear in our Q expression because it's a solid. So whether we have a pound of silver or a ton of silver, it doesn't matter. It doesn't affect the equilibrium. All right, so here we've got 2 solutions of equal concentration. Which one's more acidic? And so we can imagine a situation where we have maybe something like hydrochloric acid, which has a really, really big pKa, much greater than 1. Or we have something like hydrofluoric acid where the pKa is very big. So in other words, just saying this is that we have here we have a K that's much greater than 1, and here we have a K equilibrium, a Ka that's much less than 1. Remember that the pKa is equal to the negative base 10 logarithm of the Ka. So if we have a number that is so much greater than 1, much less than 1 and much greater than 1. So if we have a number that's small, like we would for a weak acid, so let's just write this out here. If we have weak acid, we have a really weak acid, the Ka for dissociation is going to be a small number. If we take the log of a small number, we're going to get something negative. And so this is going to end up, the negative and negative is positive, so pKa is going to be a positive number. And the weaker the acid, the more positive the pKa. So since the acids are of equal concentration, if we wanted to make it more acidic, we'd want one with a bigger Ka, or another way of saying this is a more positive, less positive pKa, right? Because the weaker acid is going to have a larger, more positive pKa. So we want one with a lower pKa. The lower the pKa, the stronger the acid. And that's because of this negative log relationship. Okay, what's ions most likely to be found in an insoluble salt? So in an insoluble salt, we want to make dissolving as unfavorable as possible to make it insoluble. And the one thing we can predict is the effective charge density on delta S of solution. So as charge density goes up, so you gotta be careful, Q is used for both heat and charge. So as charge density goes up, the delta S of solution is gonna get either less positive, it could switch from being positive to being negative, or if it's already negative, it will get even more negative, okay? Because the more charge density you have, the more you're going to align the dipoles of water in the solution. So the worst case scenario, the one that's going to be most likely to be insoluble, is a small radius and large charge. That's going to be very high charge density. Okay, so if we have something like aluminum ion or something, or phosphate ion, aluminum is really good because it's got a high charge and it's a relatively small ion, so it forms a lot of insoluble salts. Okay, what parameter varies in such a way as to make the prediction in the previous question possible? Oh, I think I already answered that. It's a delta S of solution, right? If we look at the other answers, there's not really a trend in the heat of solution with charge density. There is a trend in lattice enthalpy, but it doesn't really affect our answer, because yes, it is true that charge density goes up as our or lattice enthalpy goes up as our charge density goes up, but then that effect is wiped out by the fact that the enthalpy of hydration is going to get more and more negative as the charge density goes up. So the heat of solution, there's really no trend. So that doesn't help us. The lattice enthalpy is not really affected by charge density. So this is the key here, that the delta S of solution gets less and less favorable as we increase charge density. Number 7. Let's look at this diagram and let's see what things we can say about it if it's given, if this is the state of the system. So look at this, we can see a couple of things. One is the Gibbs energy of products is here and reactants is here. So just looking at the fact that these endpoints go like this, we can say delta G standard, which is the difference in pure energies, is going to be a negative number, right? We're downhill in energy from our reactants over to our products, right? That's products minus reactants will give us a negative number. Excuse me. We can also see that where we're at on this curve is here. Let's annotate this a little bit. If we look at this, we can see the bottom of the curve. Remember, that's the value of Q at equilibrium. We call that K equilibrium. So right away, we can say, oh, Q, where we're at, this dot, is a higher number than K equilibrium. So we can say K equilibrium is going to be less than Q. So we can just see that by comparing the bottom of the curve to the dot, which represents the state of the system. And we can either look at where the dot is and see that it's downhill in energy to go backwards, or we could just look at K being smaller than Q. We know where the backwards reaction is going to be spontaneous. Okay, so either looking at this statement here or looking at the graph, we can see we're going to go backwards. So let's see if there's any statements that match that. Indeed, delta G standard is a negative number. The forward reaction is certainly not spontaneous, actually the backward end. What about these other ones? Well, if we look at this, we said delta G standard is negative. Another way of saying that is that K equilibrium is going to be greater than 1, right? You can see this, the bottom of this curve is to the right-hand side. It's towards the products. It's a product-favored reaction. But you can use math too, right? Because we know delta G standard is equal to negative RT log of K. So the only way to get a negative delta G standard is if your K equilibrium is greater than 1. So we better circle that as well. And what about delta G? Well, delta G is equal to delta G standard plus RT log of Q. Now, delta G standard itself is negative, but to know if delta G is negative, we have to know what size Q is. We don't have a numerical value for Q, but we can still figure out the sign of delta G. We can see the backwards reaction is spontaneous. Another way of saying that is the slope of this curve is positive because the slope of the curve is delta G. And if we look at the slope of the curve at this point, we can see the slope is positive. So delta G is actually a positive number, not a negative number. Okay, so delta G standard, difference between the endpoints, products minus reactants. Delta G not standard, just plain old delta G, is the slope of this curve. So we can see over here the slope's negative, so delta G is negative. The forward reaction is spontaneous, but over here on this side the slope's positive, which means delta G is positive. The backwards reaction is spontaneous. Okay, is Q greater than 1? Yes, we can see this. I mean, we can see that we're on the right-hand side of the diagram, so yeah, Q is greater than 1. But we can also see this because we know K is greater than 1, and we know Q is greater than K. So we can see that that means that Q is also greater than 1. All right, endothermic reaction is at equilibrium. We decrease the temperature. What happens to the mass of products as a result? So once again, Le Chatelier's principal problem, but in this case, we're changing the temperature, which means in this case, we're not just changing Q, we're changing K. So the relationship between K and T is given by Van Hoff equation. So if we look at this, we know that the slope of this plot is equal to negative delta H of reaction over R. So we said that it is endothermic. So delta H of reaction is a positive number. So if we plug in a positive number into this equation, we get the slope has to be negative, right? If delta H is positive, we get this negative sign, so the whole thing has to be negative. So if slope's negative, we'll draw a graph like this. And what that means is you can divide this graph into an area of high T. And yes, it's confusing, it's over to the left, but remember this is a reciprocal axis, right? So large values of T are on the left and low T on the right. And we can see if we want to get a high equilibrium constant, it's going to be in the area of high temperature. If we go to low temperature, it's going to make K smaller. So we decrease the temperature. We went in this direction. Right? We made the temperature up. I did that backwards. Decreasing temperature is this way. Ha! Reciprocal axis fooled me too. So watch out. Make sure you actually write it down so that you don't fool yourself. So we decrease the temperature. I'm going to go ahead and erase this arrowhead there. Oops, erase the whole thing. So we're decreasing the temperature, right? We're going in this direction. And looks like if we decrease the temperature, we decrease the size of the equilibrium constant. So at equilibrium, K and Q were the same, but then we decreased the temperature. We made K equilibrium get smaller. So now K is less than Q. So the reaction is going to go backwards. It's because backwards, we're not going to have as many products, so decreases. All right, annotating a cell. Okay, so we've got this cell, and we are told that we've got copper on the left, iron on the right. So we look at the copper reaction. The copper reaction is we've got copper 1 going to copper 2. Okay, so we can see that copper, it's losing an electron, so we'll have an electron going up into here. We're piling electrons on here, that's going to make this negative. If we look at the other reaction, we're reducing iron. We're going from iron 3, it's picking up an electron to become iron 2. So we'll have an electron going this way. We're pulling electrons off the electrode, right? The chemistry is in control here since this is a voltaic cell. So if you pull electrons off, this is going to end up with a positive charge. So we'll put our charge on here. Now we're piling electrons onto this electrode. The electrode's going to end up being negatively charged. That's going to repel electrons. Where are they going to go? They can't swim. They can't swim away. The only escape route is through this wire. So we draw our electrons going through the wire. And normally we'd have a light bulb or something, and we're going to use this electricity for something. Okay, so we're partially done. We've done electron flow. We haven't done ion flow. Now there's a couple ways we can do this. We'll do the first way is if we're going through this circuit and the electrons are going in this direction, negative charge has to continue through the loop. Negative charge. So if we look at our salt bridge, it is using potassium nitrate. So negative charge would be the nitrate ion. So we could show nitrate going like this. Okay, but that's going to complete our circuit, right? So we can see in the top half of the loop, the negative charge is flowing to the right. It's going to continue flowing clockwise through the salt bridge to the left. We should also show the flow of potassium ions. They're going to flow in the opposite direction. We'll show in a second why that makes sense. Okay, well, let's just show now. If you look at the right-hand beaker, we're going from iron 3 to iron 2. So we're losing positive charge, which we have to replenish, and we replenish that with our potassiums. If we look at our left-hand beaker, we're increasing the amount of positive charge. We went from copper 1 to copper 2, and that nitrate's going to come down here and solve that problem, right? Because if we increase the positive charge, we can throw in some counter ions that are negative to counterbalance that. So we keep electron neutrality in the two beakers. Okay, so there's counter current flow inside our salt bridge. So we did the ions flowing. Now we have to do the cathode and the anode, and it's always, remember, red cat, right? You're always going to have reduction at the cathode. We are reducing our iron, so we'll call this the cathode. And we should be a little more precise. Okay, I was kind of lenient when I graded this, but the cathode is an object, right? It's the object at the surface of which you have chemistry going on. So the cathode is actually the gold rod. And same thing for the anode, that's where oxidation occurs. The anode is this gold rod. Okay, so from now on, I do want you to label your diagrams, like be specific. Don't label the whole beaker. It's actually the metal thing or the conductive object that has a surface exposed to the electrochemistry. That's the anode. Okay, we did that. Oh, we already marked the signs. Okay, so that's it. We pretty well explained how this cell works. So I made a mistake on the quiz, and then I gave you a reaction that I realized when I was writing the key is already balanced. And when I was grading the quizzes, I think that threw some of you off, and so I'm just throwing that question out. So I think I owe you a new problem, just so you can see one being solved that's not already solved. So here's another reaction of hypochlorite ion. This time we're going to oxidize elemental sulfur. Okay, so let's go ahead and write this out. We have got, so we've got to split this into half cells. So we'll go ahead and split up our sulfur going to sulfate. And over here I'll have my hypochlorite going to chloride ion. And looking at this, we can see that we need some oxygens on the left, so I'll put 4 waters over here. And I need some oxygens over here, so I'll put a water. And then looking at this, I've got 8 hydrogens on the left, nothing on the right, so I'll put 4H plus, 8H plus. Wow, I keep doing that. Woo, 8H plus. And now I'm going to do the same thing over here. I've got 2 hydrogens, so I better put 2 hydrogens over here. And now let's balance charge. So if we look at the charge on the left, I've got sulfur and water, so there's no charge. And on the right, I've got +8, -2, so that's going to give me a net charge of +6. So I better put some electrons on here to balance that. So I'll put 6 electrons here. So now I've got a total charge of 0 on the left and 0 on the right. Okay, so 2 minus, 6 minus gives me -8 +8, so that gives me nothing. Over here, I've got +2 -1, so I've got a total of +1 on the left. I've got -1 on the right, so I need to somehow balance that. If I add 2 electrons over here, then the net charge is going to be -2 +2, that's 0, and then another -1, so I get -1 and -1, so the charge balances. Okay, so the chlorines are balanced, the sulfurs are balanced, oxygen's balanced, hydrogen's balanced. We probably at this stage should check to see if it's, So it looks like everything's right. We can double check using oxidation numbers if we want. So if we're right, we did a 6 electron oxidation in the left reaction and a 2 electron reduction on the right. Let's see if that's true. So if we assign oxidation states here, this is an oxidation state of 0. If you assign oxidation numbers here, this is an oxidation number of +6. So clearly you lost 6 electrons to go from 0 to 6. So it looks like our math is right. If we look at hypochlorite, we look at that chlorine in there, that is going to be a chlorine is going to be an oxidation number of, let's see, if we make it +1 minus, so +1 minus the -2 on oxygen would give us -1. Okay, that looks like it's right. It's a +1. Over here, it's just by itself, so we know it's going to be a -1 oxidation state. So it looks like we went to +1 to -1. That's a 2 electron reduction, and indeed we do have 2 electrons being added. So our math was right. So you don't have to do that step, but if you do, it's a good just double check to make sure everything's right. So the key thing here is to say, wait, I have a 6 electron oxidation and a 2 electron reduction. So I'm going to have to multiply. I got to get least common denominator basically. So the way to do that, the easy way is 2 goes into 6 3 times. So if I multiply this whole thing times 3, I should be good to go. So I'll start off writing a big long reaction here. I've got sulfur going to sulfate. Oh, whoa, that's interesting. 2 minus. I've got 4 watt, and then 4 waters going to 8 hydrogen ions. Okay, so I'm just doing the left-hand reaction right now. So I've got this, and this. If I wanted to, I could put in that there's also 6 electrons. We're just going to cancel those in a second anyway. Now we look at this one, which remember is times 3. So I multiply everything times 3. So I have 3 hypochlorites. It's got that. I've got 3 times 2, or 6 hydrogen ions. I'm going to have 3 times 2, or 6 electrons. I'll put those over here. And on the right-hand side, I've got 3 chlorides and 3 waters. Okay, so notice the electrons did cancel because we found the least common denominator. Anything else we can cancel? Yes, we've got 6 hydrogen ions, so we should have 2 hydrogen ions. And in terms of water, we've got 3 and we've got 4. So we'll just take 1 water. So let's just write this a little more neatly. We've got a water. We've got 3 hypochlorites going to a sulfate, 2 hydrogen ions, 3 chlorides. Okay, so looking at this, let's check our chlorine atoms balance 3 and 3, sulfur 1 and 1. The left-hand side is -3. So let's write out some of this stuff. The charge is equal to -3 on the left. Charge is equal to, we've got -2, and then we've got -3, so that is a -5, but then we got +2, so it's going to end up being -3. So charge checks out. We do oxygen. We've got 1 from the water. We've got 3 over here, so that's 4. We come over right-hand side. We've got 4 in our sulfate. That's the only place, so oxygen, 4 checks out. We do a hydrogen. Got 2 from the water. We've got 2 from a hydrogen ion, so that's H equal 2, H equal 2, so that checks out. And remember we said that the sulfur is a 6 electron oxidation state. So we had 6 electrons being transferred over here, and the hypochlorite is going to be a 2 electron process, but it's 2, and it's 2 electrons being transferred per molecule, but there's 3 molecules, so that's also 6 electrons. So electrons gained and lost is the same, so that's good. So everything checks out. We're happy. We have a balanced reaction. So that's balancing a reaction. So thank you for watching the key to Quiz 5.